Okay, today I'm going to talk on a different topic, so I thought it was appropriate to have a different cartoon, just to flag the fact that I was changing. So today's subject is going to be fluid mechanics. I was asked by the organizers to cover this topic as part of the simulations, and so I will do it, but in this particular area, I have no practical expertise to offer you. I've not done most of the work, most of the kind of simulations that I'm going to talk about. And so what I'm offering you is only theoretical and not on the basis of experience. And therefore, you take it for what it's worth. Anyway, there is a big difference between stellar dynamics and fluid dynamics. Stellar dynamics, the motion of particles is influenced entirely by gravity. They follow ballistic orbits, and the physics is very clean and very well defined. If you go to a fluid, an ideal fluid of the kind that we're going to talk about to begin with, then the physics is still very well defined, but the equations of motion change because, of course, you introduce new forces such as pressure. So that ideal fluid does not obey the same equations. It obeys Euler's equations if the fluid is ideal in the sense that it doesn't have any internal dissipation. If you want to include things like viscosity and thermal conduction and other processes which are caused by diffusion within the fluid, then you really need to use the Navier-Stokes equations. But the sizes of objects in astronomy are so large that these equations are never important. So you never need to worry about those equations, and you stick with the very simple Euler equations. So there are two equations that are of fluid dynamics. There's the equation of continuity, which says that this convective derivative of the density, which is defined by this operator here, is equal to the minus the rho times the gradient, the divergence of the velocity field, and the convective derivative that's going along with the fluid element of the speed is equal to the forces applied. So this is just Newton's law for fluids, Newton's law of acceleration. And this is the gravitational potential. These notes come from when I was teaching a fluid mechanics course based on Frank Schu's book. For some reason in Frank Schu, he used this quantity for the gravitational potential. I never understood why, but that's why I'm using nu here, because Frank Schu used it when in his book, which is actually a very good book. I'd recommend it. Anyway, so this is the equation of motion. If you've got pressure forces, the gradient of the pressure and the gradient of the gravitational potential are the two forces which determine the motion of the fluid element. Now you have to worry about what the equation of state of your fluid is. Generally speaking, the pressure is a function of density, temperature, and possibly other variables as well. But if you've got a particularly simple fluid, which we call a barotropic fluid, then the pressure is a function of density only. And this is true if the gas is isothermal, that is, that the temperature doesn't change as the pressure as it moves, that it radiates away or absorbs heat from some mysterious sources which you don't have to worry about. You just assume that the gas is isothermal. Or if it's adiabatic, so there's no change in the energy content of the gas, then you know what the law is. P goes as rho to the gamma. But otherwise, if we haven't got a simple fluid, a barotropic fluid, you need an energy equation as well, which determines the heating and cooling of the gas. So the rate of change of the energy content of the fluid in the energy per unit volume or unit element this is the work done by the pressure forces, adiabatic compression or expansion, and then you've got gains and losses, which probably are radiative, mostly in the gas cools through radiation, and it also warms through being close to a star, for example. So you have those, and this is your full set of equations. Now, there's various numerical methods to solve these equations, and they fall into, or at least they used to in the old days, fall into two clean categories. There's now a sort of hybrid one, which I'll talk about later. But there are Eulerian methods, which use grids, and Lagrangian methods, which use just particles. And I'll spend some time describing both of those methods. So in the Eulerian method, you invoke a grid, and you solve the equations that we've just described, the various derivatives and things you have to approximate by finite differences on a grid, and you solve these equations through the numerically. First thing you have to realize is that there's this Courant-Friedrich condition which says that the time step has to be less than the time it takes for a sound wave to cross one of your grid cells. So if the size of your grid cells is delta x, your time step has got to be less than this quantity. And that's physically very reasonable. If you're trying to take time steps which are larger than this delta t, that means that information is propagating across your grid faster than the speed of sound, which is unphysical. It should not happen, and so therefore this is absolutely required that you can't take time steps bigger than that. And not only are you being unphysical if you take time steps bigger than that, but of course the simulations generally become unstable, numerically unstable. So this is a very strict limit. The other problem that you have when you come to deal with these kinds of fluid flows, if you have supersonic motion and you have shocks, then something happens in the fluid at the point at which it shocks, which is not resolved by the code. In fact, you can't. The equations, Euler's equations, do not contain the physics of shocks because that is essentially a micro process where diffusion or where exchange of energy between particle streams and things becomes important, and viscosity can't be neglected inside a shock. But the equations don't admit that, and so in order to get the codes to work properly, you introduce what's called an artificial viscosity. This has been done for decades. It was first proposed by von Neumann and Richtmeier many years ago, and is a well understood and well developed way of making the flows work. And you look at the divergence of the velocity field, and where the velocity field is converging, so that the flow the divergence is negative, then you take the square of that thing, call that q, and then the gradient of this q is the thing that you apply. So you add this extra term to your equations of motion. You'd only do that when the fluid is converging. If it's diverging, there's no artificial viscosity. So you want to make sure that you know which of these, what's generally happening. And in that, when you do that, the shock is spread over a couple of your zones, so that you get the velocity on one side and the velocity on the other side, and it takes a couple of zones to join from one to the other smoothly. You should also know that although there is no dissipation or diffusive terms in the equations that you were solving, once you've applied these finite difference operators, you actually introduce some of those. There's nothing you can do about it. You do find that there is some viscosity and some diffusion of temperature, just because of the way in which you apply the equations. And so these diffusive terms appear, or at least you find that the fluid is diffusing slowly for numerical reasons. But people have worked for very many years. Of course, aircraft design, car design, many terrestrial applications of fluid dynamics are very important and need to be understood, and so the process needs to have been understood very well. There are many good codes that have been developed which minimize the numerical viscosity and treat the shocks properly, and there are various piecewise, parabolic, Godunov, and other methods that have been developed, which have very long histories. We know about their behavior very well, and they are trusted codes. And people use these on grids which could be Cartesian. That's a very common form of the grid. But of course, once again, you want to use adaptive grids because in astronomy, things are not homogeneous. So these various Russian people in the United States have spent a lot of time developing adaptive grids. There's this publicly available code called ENSO, which you can download from Mike Norman's website or Greg Bryan's website. This is a code which is all singing and dancing. It will do whatever you want. It's extremely well-developed and well-tested code, which is available for anybody who wants to use it. And it does use adaptive grids on mostly Cartesian geometries. Jim Stone in Princeton has spent some time developing polar grids. And let me just show you a result so that we're not dealing entirely abstractly. This is some work that Jim Stone did with a student or postdoc, Woon-tae Kim, and this is showing you the results of gas flow in a barred potential for two different sound speeds that they're adopting for the gas. They've just got a simple equation of state, an isothermal equation of state, so that they don't have to do any of the energy physics. And I don't know whether you can see these streamlines. There are streamlines that they've drawn on this. The bar is vertical. You've got essentially a shock here on the leading edge. The bar's rotating in this sense. There's another shock on the leading edge. The streamlines come up to the leading edge here and then get deflected very strongly. And so you develop these very strong shocks. Now you can show, if it's not hard to understand, that if gas were, no pressure forces were acting, I mean, the gas is flowing in a gravitational potential like this at a speed which is, maybe 200 kilometers a second with a sound speed of maybe 5 or 10 kilometers per second. So this is a very highly supersonic flow, and in supersonic flow, pressure forces are very small, and so except where there are shocks. And so you would expect, with a mild amount of dissipation, that the gas would basically follow a ballistic orbit, and any random motion would quickly be damped out, and you can show that the streamlines of the gas would in fact follow periodic orbits if it could. But this is a set of periodic orbits in a bar potential, not totally unlike the one they're using. I don't think it's the same, but it's not very different. And Ortwin showed this yesterday, or a couple of days ago, that there's this family of orbits. It's been rotated to coincide with the vertical bar that they were using in their diagrams. There's no uniformity about how you rotate, how you just show the bars. So I turned it on its side so you can compare this with that. And you can see that there's this X2 family, which are elongated perpendicular to the bar, and then the X1 family, which are elongated along the bar. But what is clear is that gas cannot possibly settle onto any one of these periodic orbits, because gas settling onto other periodic orbits will bump into it. And the one thing that you can't have in gas, which you can have in stellar systems, is two separate flow velocities for the particles at any one spatial point. And so given that some of these orbits self-intersect, they're little ears on the end of the orbit, and so when the gas tries to follow an orbit like that, it will intersect other gas following the same streamline. So you can't have streamlines that intersect, and therefore this is why you get shocks. And the shock forms here on the leading edge of the bar, which is pretty much where people have seen dust lanes in galaxies. And you've got this elongated structure perpendicular to the bar axis, which corresponds to the location of this X2 family, where flow stops. And the shock causes the gas to lose energy, and the gas, when it loses energy, and it's also, since it's asymmetrically distributed about the principal axis of the bar, it also loses a bit of angular momentum. The average time average of the position of gas elements relative to the axis of the bar they're not coincident. And so there is a torque between the gas and the bar, and the gas loses angular momentum, and the bar should gain angular momentum. These people don't worry about that. This is massless gas, but the bar should speed up a little bit as a result of losing the angular momentum to the gas. And the gas gradually flows in and builds up a concentration on this ring here. If you have a higher sound speed, this is 20 kilometers a second, that's 5. If you have a higher sound speed, things are slightly different, and the shocks are not quite so well defined, but the behavior is the same. 20 kilometers per second is a very high sound speed for a bar flow. And there's some evidence that this really does happen in galaxies. This is an image of NGC 1512. This is a nice barred galaxy. You can see the dust lanes on the leading edge of the bar where the shocks are predicted to form in those hydro simulations. Dust lane is where the density is high, and it was Kevin Prendergast in 50 years ago who pointed out that the location of the dust lanes is a good indication of a shock. But if you zoom in with the Hubble Space Telescope and look at the nucleus of this galaxy, you see a tremendous ring of star formation, which is here you see the dust lane coming in from the bar. So the bar is way enormously larger than this image that we're seeing here. We're just zooming in right on the very nucleus of the inner part of the bar there. And this is the dust lane coming in this side and dust lane coming in that side. And you've got this enormous ring of star formation. So there's clearly been a build-up of gas density here, which has triggered a formation of these stars. And you can tell immediately from the fact that there is an overdensity of gas at this radius, and compared with inside of that the gas does not flow further inwards. At least the majority of it. Some gas is clearly going to flow further inwards, and then maybe the mechanism for it to flow inwards is still under discussion. But you can see there are interesting dust lanes inside this region here. So clearly there is some kind of transport of gas going on, but the majority of it is stalling at this ring, and only a small fraction of it goes in any further, and you get this big burst of star formation. Okay, so that was Eulerian methods. Now, there are the Lagrangian methods is another way of approaching fluid dynamics. And the most popular method by far is smooth particle hydrodynamics. So I'll spend a little bit of time describing that. There's a nice review of smooth particle hydrodynamics in the annual reviews by Volker Springel in 2010. The fundamental principle of smooth particle hydrodynamics is that each individual particle is no longer a point mass, but is smeared out over a finite volume. And it has a density profile which is given by this function W of psi, which is psi is the variable which is the distance from the center of the particle, and you've got to make sure that this function is properly normalized so that when you integrate it over the entire sphere up to the limit at which it goes to zero, W goes to 0, it integrates up to 1. so that it doesn't change the total mass of the particle, for example. And once you've defined that kernel, you're then able to define all sorts of properties for the fluid. For example, the density of the fluid at some field point X is the sum of all the different particles present in the simulation, and they're at the various points xi, and the distance between between the field point and the point at which you're interested, at the center of the particle, determines how much that particle contributes. So you form a weighted sum of all the different particles contributing to the density. If you want to define the velocity, you do the same kind of thing. You weight the velocity by the value of this kernel function, and to define a density-weighted velocity at that particular point in the fluid. And you can do that for pressure or any other term that you want to, anything else you want to do. If you want to compute a gradient of a quantity Q of any kind, then you go through a similar procedure. You take the gradient operator inside, and you take the gradient of this kernel, which is obviously something that you know ahead of time. You can you know what this function is as it's a simple differential problem. So that gives you the gradient of that value of the quantities. And a good example where you'd need to do this would be with the pressure. Yeah.
It's a single, in small particle hydrodynamics, you use single kernel, you use different kernels for different kind of particles.
Well, that's an excellent question. I mean, generally speaking, you use the same functional form for the kernel in any simulation, but you can make the width of that kernel adaptive. You can make it small in regions of high particle density and wide in regions of low particle density. And people do that, so thank you for asking. So typically, the kernel width is chosen so that you've got between 20 and 50 particles overlapping at any one point, so that you've got a nice definition of all these fluid quantities. And then you accelerate the particles according to the gradient of the pressure that you've just defined. And then as I said, I've told you how you can calculate the gradient of the pressure, the gradient of the gravitational potential, and you still need to put in this artificial viscosity, which has to be, which you also have to compute if you're going to do the shocks right. Now this. It can be proved, and mathematically it has been proved, that smooth particle hydrodynamics really does solve the Euler's equations properly in the limit of infinitely many particles. But of course, you have to use only a finite number, and so this is some approximation to those equations, a different approximation than the grid, but nevertheless it's an approximation. So this smooth particle hydrodynamics has been used for many different applications. You can look at Joe Monahan's website to see some of the interesting things he's done with it. But I'm going to focus entirely on its application to galaxies. And the first thing I want to do is to show you that there's really not a lot of difference in the way, if you do the same kind of problem with smooth particle hydrodynamics and with grids, and you don't try to put in anything fancy like star formation and energy input and all that kind of thing, you get the same answer. So Isabel Perez did this in 2008. She compared the gas flows for a model galaxy of NGC 4123, which Ben Wiener did for his PhD thesis, and that we computed that flow using a Godunov method in 2 dimensions, and then Isabel computed the same flow in 3 dimensions using smooth particle hydrodynamics, and then in this paper she just studied the velocity field that she got from the 2 different methods and showed that there was pretty good agreement. So that's nice to know. Smooth particle hydrodynamics has got many, many strengths. Phil Hopkins, in his paper in 2013, which I'll get to in a minute, started out by listing a long laundry list of reasons why smooth particle hydrodynamics is a good scheme to use for galaxies. If you want to know all the reasons, then Phil sets them out there. Obviously, smooth particle hydrodynamics concentrates your numerical resources where the fluid density is high, and there you get better resolution and better representation of the behavior in those circumstances. And another big advantage, which has made it almost overwhelmingly popular, is that you can include self-gravity of the particles, which is more difficult to do if you're using a grid scheme. You can include self-gravity through some kind of direct method, tree codes or whatever, very easily, because you've already got the positions of all the particles. So you can make the gas self-gravitating, combine it with stars in a rather simple way. And this was first done by Berendsen, I believe, and Fuchs. But the problem with SPH is it does have some serious weaknesses. The first one I want to stress is that unlike grid codes, which have been developed very carefully to reduce numerical viscosity, SPH has very, very high numerical viscosity. And you want to be very concerned about that. I'll show you what the consequences of numerical viscosity in a minute. And it also doesn't have very good performance on things like Kelvin-Helmholtz instabilities, and I'll describe that too. So this is a simulation that was done by Heller and Schlossman. I just chose from random. I didn't want to pick on them in particular, but this was published back in '94. And what they did was they had a disk of particles, gas particles and star particles, which was globally unstable. It wanted to form a bar. And what you're seeing in this series of images here is the time evolution of just the gas particles. Underneath that, there's a bar forming in the stars. And you can see where the bar is, obviously, from the way it's behaving. But I think time is running down the page like this. But from time 4 to time 14, which is all they're illustrating here, the gas distribution changes from being roughly uniformly distributed over the grid to almost over the galaxy, rather. There's no grid, to almost everything concentrated right in the middle. And this inflow rate, which is physically reasonable. We discussed what the inflows in bars are important, and that really does happen. We know from observations. We can see the gases flowing inwards, but this rate at which the entire gas distribution in the galaxy ended up in the central blob is completely insanely fast. And that is inflow rate is because of this numerical viscosity. And the reason is that you've got gas streams flowing in opposite directions along the bar. And because of the finite kernel size, the stream that's going one way is talking to the stream going the other way when there shouldn't be. And that loss of energy caused by the two streams overlapping just causes everything to drop down to the middle and stop. So this is the numerical viscosity, which is rearing its ugly head in a very unphysical, unrealistic way. So inflow does happen and should happen. There should have been shocks in this thing, but it was being accelerated by many orders of magnitude by this numerical viscosity. The other thing you should worry about is these Kelvin-Helmholtz instabilities. A Kelvin-Helmholtz instability, it reminds you, is you have fluids of two different densities. The wind blowing across the ocean is the typical example. As the wind blows across the ocean, it tends to raise waves on the surface, and that is described by the Kelvin-Helmholtz instability. And if you use a grid method and you have a flow going one way of low density material and a high density material going in the other direction, you introduce these waves which are properly captured in grid methods. But when you try and do that with smooth particle hydrodynamics, zip, you don't see anything happening. And the reason was pointed out by this team, Eckert et al. From Zurich, but there was a whole cast of characters who got their fingers into this particular paper from all over the world. And the reason is that if you look in excruciatingly detail right at the surface here of the dense fluid compared with the low density fluid, you see that the particles have arranged themselves on lines. the forces between the particles introduce a spurious pressure which separates them into these lines, and then they can quite happily move without and cause the gap, and so the instability doesn't develop in smooth particle hydrodynamics. And that's important. It really affects the way things behave. So now, 2007 was when Gertz et al. Pointed out that this problem existed, and of course the smooth particle hydrodynamics people have responded by developing fixes that take care of it. The two most important suggestions came from Reed and Hayfield and from Hopkins, and let me just show you a movie to illustrate the difference between doing. It's going to come up. Hello, you awake? Seem to be doing anything. Just a minute. Let's get rid of that. Don't want that. Huh. What? Pardon me? Well, it's playing.
I'll do it again.
Okay. It's not that big a movie. I don't know why it won't show. It was showing just before I started this morning. Open with QuickTime. I really do want to show this movie. I do want to show it. Here we go.
Now you have to make several instances.
Yeah, probably. It's too big for my window, so I have to, first of all, do it there. All right, here we go. So this is the original gadget SPH simulation. What it's showing you, and I'll let you watch it right to the end and then I'll restart. Let's go back to the beginning. This is a blob of high density gas, exactly the same conditions moving through low density gas, and the speed of the blob is supersonic. So it should actually not only suffer from Kelvin-Helmholtz instabilities, but it should also disrupt. And so what you're seeing here is more or less the same to begin with. If both codes are doing the right thing to begin with, let's pause it at this point here. First of all, as the flow, you can see the bow shot developing as it goes to upstream. As the gas flows around this object, Bernoulli's equation tells you that there should be low pressure on the sides here, so the blob gets extended in the direction perpendicular to the flow, which is what should happen. Both codes did that. But what doesn't happen in Gadget, which does happen in this modification, which they call Changa, to SPH, is that the Kelvin-Helmholtz instabilities should cause this surface over which gas is flowing to disrupt, and it just doesn't. Whereas in the Changa simulation, it does. And so this is turns out to be rather important for the astrophysical applications. That you can see the blob has almost completely disintegrated as a result of those Kelvin-Helmholtz instabilities, whereas although it's changed shape, it's still intact in the original gadget. Okay, let's go back. Now I've got about 6 copies, as you said, of the movie. Let's try and close them all, otherwise it's going to slow me down. Okay. Back to the... My computer is rather slow. It's nice and light to carry, but it's not very powerful. There we go. All right. So, the weakness, SPH has its problems, although as you saw from the Changa implementation, they have at least fixed the Kelvin-Helmholtz problem. But because Springall was aware, I think, that SPH had various numerical difficulties, he wanted to introduce a new code, which is a hybrid method between a Lagrangian and Eulerian method. So fundamentally, what this is a collection of particles, or mesh points rather, that move with the flow. And then he does a process called Voronoi tessellation between those nodes which are defined. And Voronoi tessellation just computes the shortest distance between 2 particles and puts a grid boundary at that point. And the geometry of the grid cell is just determined by the shortest distance to the next particle in all coordinate directions. And that's what and it has whatever shape it has, because the particles, of course, are not in the same arrangement all the time. It's no longer a regular arrangement. So this is a hybrid method, but the grid essentially moves with the flow. Now, it hasn't been made publicly available, and so Springall, quite naturally, since it took him a couple of years to write this code, is keeping it to himself and his friends to milk it for quite a number of publications before he makes it public. So nobody else can get hands on it without writing the same code themselves, or waiting until Springall makes it available. But the results from in galaxy formation simulations, which they have used it for, are very different from, or at least quite significantly different from those from SPH. And the 2 problems of numerical viscosity and Kelvin-Helmholtz instability really are driving why there is a difference between these 2 codes. I mean, they've largely compared with the old gadget, which is a little bit unfair since people who use SPH now have fixed it to fix the Kelvin-Helmholtz problem, but the numerical viscosity is still present. And in the old simulations of galaxy formation with SPH, the gas settled too strongly to the center of the galaxy. The baryonic component was too concentrated, and that was partly the result of numerical viscosity. And the fact that the blobs of gas that were falling into the hot halo of a galaxy were not being disrupted by the Kelvin-Helmholtz instability also led to different distributions of gas in the models that were formed. And so this code is significantly better, at least that's what it's claimed to be, over SPH in those sense. Now, for the last part of today, I'm just going to talk a little bit about the interstellar medium and how you try to manage that. These images from the Herschel website of M31 showing you in different wavebands, optical, infrared, X-rays, blah, blah. And this is a composite image of all of those. And the interstellar medium is being picked out in the infrared by Herschel, which is clearly looking at the warm gas. And you can see that gas distribution is far from uniform. And it's quite definitely not the ideal fluid that the Euler equations assume. Most of the mass is in the dense clouds of gas, which have sound speeds of less than half a kilometer per second. Whereas the turbulent speed of the interstellar medium is between 5 and 12 kilometers per second, depending where you look. And so the motions of these clouds are highly supersonic within the medium that the interstellar medium. Then in addition to the dense clouds, of course, you've got warm and hot gas, three-phase medium that you learn from your textbooks in ISM. It's got magnetic fields, it's got cosmic rays, and both of those things add pressure to the fluid, as well as the turbulent speeds, which is equivalent to the pressure. These turbulent speeds are stirred up by supernovae, stellar winds, spiral arms, heating, magneto-hydrodynamics instabilities, such as the magneto-rotational instability, which must be present at some level in galaxies, is stirring up the ISM. And in addition to all of this, the gas is trying to fragment and form stars in a very non-uniform way. The gas is being heated by the radiation from those stars and cooled by various molecular and atomic lines, Bremsstrahlung if it's very hot, dust if it's very cold. And so all of these mechanisms are important. It's depending on the chemistry of the gas, the cooling rate changes. Then, in addition to once you've got this feedback from the stars, you might get supernova explosions, whatever that drive gas out of the plane. The gas is falling into the plane from outside, and all of this is going on scales which are far too small for you to be able to resolve in any reasonable simulation. And there was the Canadian cosmologist Bill Unruh ruefully remarked that when you're trying to understand galaxy formation, from the early universe right through to the point at which the first stars form, the physics is really well defined. We understand how that physics behaves. We know how to calculate it. It may be a bit complicated. It's a bit like watching a game of chess that you don't quite know what the rules are to start with, but you think you should be able to figure it out. It's a very elegant game. But the moment star formation happens, the rules change from being a nice, elegant game of chess to mud wrestling. And that was how he described it. And you have somehow to cope with all of this mess. Now, how you do that is a vexed question, and I'm not going to spend a long time describing all the different methods because that would take me far too long. But the interstellar medium, point I want to get across is the interstellar medium is far too complicated to model in detail. But if you're interested in doing galaxy dynamics, really only one physical process is important. The only one that matters is that the gas damps random motion. If you stir the gas at all, then you set up a turbulence in the interstellar medium, and that turbulence cascades, as Kolmogorov taught us years ago, down to smaller scales as time goes by. Even in an ideal fluid, the turbulence gradually cascades down. As you look in behind the wake of a boat, when you're riding on a boat at some point, you can see these turbulent eddies streaming off in the wake of the boat. They gradually, the eddies cascade down to smaller and smaller size, and eventually the eddies are small enough that dissipation can get rid of the energy. And that same thing happens in the interstellar medium. Whatever you're talking about, the kinetic energy of the turbulence eventually gets dissipated. It goes into the thermal, to heating the gas, and that gas can radiate away the energy. And so this is the most important physical process, is that once you stir up the interstellar medium, it tries to dissipate that energy and revert down to a nice regular flow pattern. And so the result of that is that stars form in molecular clouds, and those molecular clouds move on nearly circular orbits. And this is of importance to galaxy dynamics. All right. So the primary physical process is inelastic collisions between clouds. Those are the ones that damp. And they damp down the peculiar motions down, and especially in converging flows. And various people have said, aha, well, I now know this is the important physical process, so maybe we don't need to do the full hydrodynamics. And so various other schemes have been discussed, and the most popular of the other schemes is sticky particles, but there are several more. Heike Salo and Bourneau and Combe are some of the big practitioners of the sticky particle approach. And let me just show you, this is Salo's group. They're trying to model the galaxy 4245. This is not an evolutionary sequence. You don't know for sure what the pattern, in fact, don't know at all what the pattern speed of the bar is just by looking at it. But they're trying to model the gas flow in a galaxy, which they believe is resembling this 4245, and they're making the bar rotate at different rates in each of these images, and then they're going to argue that some particular value of the bar rotation rate gives the best match to the data. But I myself have taken an even bigger shortcut in terms of dealing with the with dissipation in the gas. If you do a simulation, as I did with Karlberg back in 30 years ago, the spirals begin to form. This is just 2 dimensions. The spirals begin to form, but after something like 10 rotations, the random motions that have increased as a result of the spiral activity, and the spiral activity fades. But if I introduce new particles on circular orbits, then that allows the spiral activity to continue indefinitely. And this gives a natural explanation for why you get spiral arms in gas-rich galaxies, and if you take away the gas from a galaxy, it becomes a featureless disk, S0. So this is a very attractive explanation, and all we had to do in order to get the gas physics in was to put new particles in on circular orbits. We didn't do anything else. So we weren't really doing gas physics, but we were just mimicking the effect of dissipation. And if you don't believe or don't like taking a shortcut like that, the full-up simulations done by Gertz et al. In 2010, this is the stellar distribution, this is the gas distribution. They've gone through the whole shebang of forming a galaxy in a cosmological context, and this is a convergence test. There's not a time sequence. They're showing the effect of changing some of the numerical parameters, which does have an effect, as you can see, particularly on the gas. This is the stellar distribution, and this is the gas distribution. And they don't even bother to say very much about the spirals. They just say, oh, well, yeah, we've got spirals, full stop. But they get spirals because they have dissipation. Now, the result of self-gravity and of dissipation is inevitable that you will get a condensation of material. Even if there's no numerical viscosity, you've got a perfectly inviscid code with no numerical friction whatsoever, you can still redistribute angular momentum by gravity torques, and that will allow your gas to condense down into denser structures. And so this is an inevitable consequence of just including gravity with dissipation. And you can't avoid it, and it happens in everybody's simulations. So, and it happens in nature too. And in reality, of course, the gas clouds eventually fragment into smaller objects. They begin to form stars, and the residual gas gets dispersed by the energy input from those stars, and it goes back out into low density material. But we have absolutely no ability yet to model this process in detail. People who work on the formation of individual stars without worrying about the rest of the galaxy are still struggling to get this particular part right. So it's no surprise that if you're trying to do a whole galaxy at once, you can't resolve any of this and get the physics right. So they introduced these ad hoc rules, which are known as star formation and feedback. And so these rules are motivated by observations, and there's, as the observational data improves, these rules are improving, but they also tune these rules to achieve the outcome they want. That's an important thing to bear in mind, that just because they get the right answer, you don't know that they've done it right. They've tuned their parameters in order to get the right answer. So we don't know, for example, at what density you should begin to start forming stars, what fraction of the gas of in a particular region a cloud goes into the stars. I mean, we have some empirical data that might tell us that, but it's typically around 10% or something like that, but you don't know for sure. And then you don't know how much energy to return to the interstellar medium from the winds and supernovae from those stars that you've just formed. And when there is, you know that there is some energy returned to the interstellar medium, that's an established fact, but we don't know whether that energy should be input into the surrounding gas just as thermal energy, or should it be in some kind of kinetic energy of bulk motion. And then if you have a whole burst of supernovae in some part of the galaxy, then the simulations show that you get outflows. And we do see outflows in high redshift galaxies and even in M82. I think it's M82, right? You see these outflows from a burst of star formation. But how much gas should you put into that outflow? How much of it stays in the disk? We don't know. And the answers to all these questions and many more are just best guesses. And these things have to be guessed at in order to run a simulation. You also want to do chemistry. You know, the gas has been through stars, so it's been astrated. That's an old word I haven't heard for a long time. But it's been astrated, and so the material that comes out from stars contains metals where when it went in, it was pristine, or at least in the first generation it was pristine, but it always comes out with more metals than it went in. And so you can build up a distribution of heavy elements in the galaxy by this process. And we know that's how it happened. You can track, if in the simulations, the distribution of metallicity in the gas, and then model the formation of the metallicity distribution of stars. And you should bear in mind, of course, that the metallicity affects the cooling rate of the gas, so that changes your physics rules. You have to include additional cooling if you've got metallicity. So it's totally remarkable to me that when you have made an attempt at guessing rules for all of these processes, that something physically reasonable comes out at the end. But here, for example, is the work by Roskar, which I think Ken has already showed. But they're modeling the formation of a disk galaxy, doing cooling, star formation, chemical evolution, and the gas dynamics and stellar dynamics all in one simulation. But they haven't included the fact that there is a whole universe around it. It's an isolated galaxy that they're simulating. But nevertheless, they've done all of this using the gasoline code from the University of Washington, which has all the bells and whistles which I described before. And what they was doing was studying the consequences of radial migration. You see the effect, the metallicity spread. This is the age metallicity relation. This is showing you about the formation, the radius of formation and the metallicity distribution of stars in the solar neighborhood. This is showing you the metallicity distribution function. And these things match data reasonably well. So it's truly remarkable that they were able to do that. Okay, so that brings me to my conclusions. If you want to do if you want to form galaxies and you want to evolve them, gas dynamics is crucial. And you can't avoid doing, you must do it, even though I spent most of this week not doing it. I know that it's an important important part of galaxy formation and evolution. And I'm not denying that it is, it's just that I much enjoy working in circumstances where I understand what the rules are. But dissipation is vital to form disks. You will never make disk galaxies unless there's gas dissipation. So that's a vital part. And gas dissipation also drives secular evolution in disks. It maintains the spiral activity. It forms the rings, the inner nuclear ring that I showed you to begin with, but outer rings and inner rings are also formed. John Cormandy will tell you at great length, if you give him the opportunity, that it will make pseudobulges. And there are many other aspects of gas evolution which are important for disk dynamics. The problem is that when you try to deal with this, that you have to implement gas dynamics, or at least the evolution of the gas, through plausible rules. And although you've chosen your rules as carefully as you can, and you've tuned them to match the data, you're no longer simulating the physics, you're just playing with rules. And I'll stop there.
So your recipe for plain visible galaxy evolution.
It's not my recipe.
Is to do both things together. So
yeah,
not only.
I don't do any of this.
So but you don't need it because you don't need it. So my point is by running a pure n-body code.
Oh yes.
The gas, can we get
this one?
As you have shown to us during this week, we have let's say plausible results. We can compare results with observation, so we can gain understanding of what is inside every process, or at least part of the understanding. Right. So in principle, one would say, I don't need a gas.
Well, I tried to say that I recognize that gas is important. But for this kind of behavior, in order to get this right, the only thing you really need is dissipation. And you can put that in by hand. You don't need to do the equations of fluid dynamics are nowhere. They're not necessary. And that's also really true still. I mean, in these cosmological simulations that put the whole 9 yards, all the star formation feedback and metallicity evolution and everything else, they do try to do the fluid dynamics as well. They put in laws of cooling and energy equilibrium, and then they compute the flow. And if you want to work out where to put your stars in the disk, you really need to be cooling the gas and putting it in a deterministic way. We just chose a rule to do that. So we're just as guilty as others in choosing a rule, right? But it's just that we didn't bother to do that calculation of all those more complicated physics. We recognized that the only thing you need to include is dissipation. Yes? For the chemical evolution, yes, of course, yes. No, I completely agree.
I wanted to say something because I think it's important to note that hydrodynamic equations have one major drawback, is they're not Galilean.
Galilean invariant.
They're not. If you like, in particular, if you have a problem that you add like fault motion on top of it, you get different results.
I think that's unlikely if it's a well-tested. I mean, the kind of codes that are used for aircraft design and what have you do not have flaws like that. If somebody has written a new code for astronomy and it does have a flaw like that, then they obviously didn't do it right.
There might be fixes to this, but basically suffer from that. That's why a lot of people prefer SPH codes, particularly for anything that's very dynamic.
I don't want to have a long argument about this because I don't know enough about it. So you could be right. Ortwin.
But one important aspect is being aware of all the limitations. But then when you try and understand which of these limitations are really relevant, or whether you can actually get an answer that's pretty okay, with some uncertainty perhaps, but fundamentally okay, given your setup. For example, in this problem, when you think of accretion of gas on the disks, then you have an obvious heating mechanism, which is the accretion energy. You have a second heating mechanism, the star formation. And that's sort of more relevant on a global scale, and I think you can estimate this, and then you can sort of see whether your temperature is reasonable.
Oh, yes, of course.
You see that in higher galaxies where you can estimate this. You know, that these estimates come out usable.
Oh yeah, I mean,
there's some aspect of these calculations which one can trust better than others.
yeah, well, obviously we know. I mean, nature knows how to do this. It makes galaxies and it evolves galaxies in a way that we can observe. And so the observations tell us that the way in which we should be structuring our codes. I don't disagree with you, Ortwin, but I think, you know, the fact that we are able with these rules to get something which looks even approximately like a galaxy is telling us that we're not doing it complete. It's not complete nonsense. Yeah. Ken.
I was a bit surprised that having watched the subject for a long time, I was a bit surprised that sticky particles became so unfashionable as they did. Now, I'm just wondering why that happened, because I would have thought most of this physics you could put into sticky particles. And allied to that is a question. If you have a sticky particle scheme, does it go Helmholtz?
I don't think the sticky particle people can do the Kelvin-Helmholtz instability. I don't think they can. But I think what they're right is that they have recognized, as Karlberg and I recognize, that the only thing that matters really is dissipation. As the flow converges, you should get rid of some of that energy